So in the last set of lectures, we just had an introduction to eigenvalues, and we've been able to calculate some for 2x2 and 3x3 matrices. We're now going to see how to find eigenvectors, and we're also going to go on to see some of the uses of eigenvalues and eigenvectors, and we'll see what they're for. In particular, diagonalizing matrices. So a little recap. You have a square matrix, an n by n matrix, and we call lambda an eigenvector and x an eigenvalue. Some people say an eigenpair. You can have an eigen anything, it seems. So the point is that ax equals lambda x. And in general, even if the matrix A is real, we allow the eigenvalue and eigenvector to be complex. And you saw that we get a polynomial equation to solve for the eigenvalues. So obviously they might be complex, and we will actually make complex matrices in electrical engineering. We'll need them for doing alternating current circuit theory. So we'll just stick to real matrices, but remember that the eigenvectors and eigenvalues might be complex. So this funny C means a set of complex numbers, and C to the n means complex vectors. So x is an element of the set of complex n vectors. So the thing is, if the eigenvalue is complex, the eigenvector x might be as well. If x is an eigenvector, then so is any multiple of it. So twice it, 3 times it, minus 5 times it are also eigenvectors for the same eigenvalue. And we count them more or less as the same eigenvector. It's really about the direction. You just can't have 0 as an eigenvector because that's silly. I mean, a times 0 equals 0, and lambda's kind of irrelevant. So x has to be a non-zero vector. This says if A is real, a real n by n matrix, then it has n eigenvalues, allowing for them to be complex and also possibly repeated. So you can have, double roots of a quadratic, for example. Okay, so just to recap the geometric explanation, that a matrix A, a 2x2 matrix, moves vectors around in a plane. It takes 0 to 0, but it can rotate or it can stretch or shear. And an eigenvector is a direction that when you multiply by A, it's in the same direction. So if that's x, that's ax. So it really is stretching along that direction rather than rotating it. Complex eigenvalues, of course, a little bit harder to understand, and in practice it tends to be if there's some kind of rotation going on, there isn't a real eigenvalue and eigenvector. So if the eigenvalue is bigger than 1, it stretches and makes everything bigger. If it's less than 1, it shrinks. Well, as well as a geometric explanation, it has an algebraic explanation. And the point is that if ax equals lambda x, we've seen that that means A minus lambda I, where I is the n by n identity matrix, that must be singular, because otherwise there isn't a non-zero solution to ax equals lambda x. So first of all, we can find the eigenvalues by solving det A minus lambda I, called the characteristic polynomial. And it always turns out to be a polynomial of degree n. So we solve that, we get the roots. They might be complex, they might be multiple, but we just have to solve a polynomial equation. We've seen some special cases. If A is diagonal, the eigenvalues are just the diagonal elements, nothing special. In fact, if it's triangular, upper or lower triangular, we saw also that it's the diagonals that give you the eigenvalues. Actually, it's kind of traditional to list the eigenvalues in increasing order, just if you want to give them a numbering. I don't kind of really necessarily have a numbering, and that doesn't work for complex. But the eigenvalues are just the numbers on the diagonal of any upper or lower triangular matrix. It turns out that if A is symmetric, in other words equal to its transpose, so everything either side of the main diagonal, they're mirror images of each other, it turns out in that case, and it's quite an important case, that all the eigenvalues are real. If you have a general real matrix, the eigenvalues could be real or complex, but if they're complex, because you're solving a polynomial, they'll come in complex conjugate pairs. So they'll be of the form something plus I something else and something minus I something else. In other words, complex conjugates together. And that's really just because of the quadratic formula having a plus or minus square root in it. So whenever you've got a complex pair, they come as conjugates. They come in twos. So you can't kind of have let's say 2 real and 1 complex eigenvalue of a 3 by 3 matrix. It would have to be, you know, a real and 2 complex or 3 real. So let's compute some eigenvalues. Here's a matrix. Well, it's not quite upper or lower triangular. It's not too bad though. So we don't expect quite the diagonal necessarily. So we work out the determinant of A minus lambda I. In other words, we get 4 minus lambda, 3 minus lambda, 1 minus lambda on the diagonal, and then we start working out determinant. Lucky thing is that we can use these zeros here. So we've got 4 minus lambda times the determinant of this with lambda taken off the diagonal, which is 3 minus lambda, 1 minus lambda, minus 1 times 0. So it does work out quite easily, and it's actually just 4 minus lambda, 3 minus lambda, 1 minus lambda, just as though it was diagonal, and the eigenvalues are the solution of that. They're 3, 1, and 4, even though it wasn't lower triangular. Suppose we know that A has an eigenvalue lambda, in other words, det A minus lambda I equals 0. Then we want to find the eigenvectors. So how do we do that? Well, we have to solve a system of equations. And the point is we know what lambda is, so we know what A minus lambda is. So we're trying to solve this matrix in the brackets times x equals 0. And of course the point is, if A minus lambda I was invertible, the only answer would be 0. We'd have a unique solution. So kind of the whole point is we don't have a unique solution. So we've got infinitely many solutions. And well, we'll see that will mean there's at least one vector x that's an eigenvector. See what happens. So that's a singular system, and we can do it by Gaussian elimination, or however we like, really. So I mean, if we find that A minus lambda I was non-singular, then obviously we got the characteristic equation wrong, or we got the wrong roots. So we'll have an arbitrary unknown, you know, like the typical Greek letters that we got before. And of course that's not surprising, because if x is an eigenvalue, then any multiple of x will be an eigenvalue too. So you've got an x, then c times x for non-zero c is also a solution. That will come in as one of the unknown constants when we solve the system. Okay, so here's a little example, a 2 by 2, and of course we know the eigenvalues are 1 and 2 because it is actually upper triangular. So lambda, let's call them lambda 1 and lambda 2, just in order. Okay, so now we look at A minus lambda I, first for lambda 1, which is 1, so we subtract 1 from the diagonal. So A minus lambda I, in the case of lambda equals 1, we just subtract 1 from the diagonal. 1 minus 1, 2 minus 1. And look, that matrix is obviously singular because it has a row of zeros. Or if you like, sorry, it has a column of zeros. Or if you like, the first 2 rows are the same. So they're obviously multiples of each other. But when it comes to solving that system, you see, we just say, well, we can't find x2. So x, well, I mean, sorry, let's take the last equation says x2 equals 0. So that's what it is. But that means that x1 can be whatever you like. In fact, you'll see these equations both say x2 equals 0. So x1 can be what you like. So you call it something, call it t, if you like t. And so the solution, the kind of general solution of this is vector t0 for any t that you like. Earl Grey, English breakfast, even Lapsang Souchong. So then you have the eigenvector. I mean, so we could say 1, 0 or 2, 0, kind of any kind of t you like there. So that's the eigenvector for this eigenvalue. And now we have to do the other eigenvalue. Lambda 2 was 2. So we solve A minus 2i. And you subtract 2 from the diagonal, because it kind of does the opposite thing. It makes that 0. And so the last line says 0 equals 0. So big deal. We can't find x2. So we set x2 to be the unknown parameter t. I mean, notice I'm not using lambda because lambda is really traditionally the letter for eigenvalue. Goodness knows why. It's a kind of L. It's not kind of the first letter of eigenvalue, is it? Anyway, yeah, so we use t, and then x2 is t. The first equation says minus x1 plus x2 equals 0. So that means x1 equals x2, and so the solution is t. Right? Any multiple is a vector 1, 1. So the eigenvalues and eigenvectors are 1, that's the eigenpairs, the eigenvalue 1, the eigenvector is any multiple of 1, 0, and any multiple of 1, 1.